Good. I think we can start. So thanks everyone for joining today to this new seminar from the Cambridge Ellis unit. Before we start, I would like to thank the sponsors of the unit. We are really grateful for their support. And today's speaker is Rika Antonova. She's currently a postdoctoral researcher at Stanford, but she's very soon going to start a faculty job here at Cambridge. I think she's starting in August. Rika, she's, as I said, a postdoc at Stanford. She has been the recipient of an NSF Computer Innovation Fellowship, and she completed her PhD on data efficient simulation to reality transfer at KTH. And before this, she did a master at the Robotics Institute at CMU. Before that, she was a software engineer at Google. Today she's going to be talking about enabling self-sufficient robot learning. I'm going to stop sharing my slides, and Rika, you can start sharing yours. You can unmute yourself.
Okay.
Yeah, good.
Yeah, let me try to share the right screen. Hopefully. Okay, so hopefully we can see.
Yeah, that's good.
The title slide. Okay, right. And transition. We'll organize this here. Okay, and just to verify, the slides do transition, right?
Yeah, we can see them.
Okay,
clearly.
Perfect. Okay. Thank you for the introduction. Yes, so today we'll be talking about enabling self-sufficient robot learning. And the one interesting thing that we have considered now is this statement about a personal robot being potentially the personal computer of the 21st century. At the beginning of the 21st century, we have already seen some very impressive demos, and these demos heralded the so-called robotics revolution. But what is the catch? We're still waiting for the robots to arrive, to work with us in everyday environments. And the catch is that some of these very impressive demos have been teleoperated or meticulously tuned or hard-coded. So we know that there is a bit of hardware out there that is already quite capable, but we still need to figure out how to work
I asked this to Jay because
with the algorithms that can actually enable autonomous operations for the robots. Now transitioning to the 2020s, you can see much more impressive demos coming out these days for full-body humanoids, achieving very interesting and intricate manipulations. And actually, this is not just one or two or three companies. There's a whole number of humanoid companies being actively funded right now. And so the question after seeing all of these impressive demos is the personal robot ready? Did we miss the revolution? Did it already happen? And of course, the catch is just as before that many of these impressive demos are teleoperated. So while, again, the hardware is on the way to getting there and is starting to get more and more affordable, actually, in order to operate with intricate tasks or handle deformable objects or work in unstructured environments, what people usually do is they build a teleoperation system of various kinds, and with that achieve these impressive abilities for the robots. So there is still development in autonomous learning. So for example, the robot learning is on the rise with highly parallelized simulations, with also being able to learn from supervised data sets in a supervised way from large-scale data sets, and also ability to leverage various machine learning frameworks in order to be able to parallelize the learning and also have the learning happen end-to-end by leveraging deep learning, for example. But I would argue in this talk that actually there is one missing piece still, which is self-sufficiency. And I will explain on the slide what I mean by self-sufficiency. So first of all, robots or learning algorithms that are running on the robots, they need to be able to detect the limitations of the models, the data, and the simulation by interacting with the environment directly. So it's not enough to just take in the data that has been given to them and run with it. Also, they need to adapt in data efficient ways. So, for example, if you fail to solve the task, you need to be able to, within real time, with operating with the objects that you already have in the environment, be able to correct your mistakes. And ultimately, these systems need to explore to learn completely new skills that are absent from the training data. So these are some of the things that I would consider kind of as a necessity for being self-sufficient, like, you know, the person going into an unknown environment, being able to adapt to that environment. Robots need to be able to do that as well. Okay, now let's step back and see what is the big picture of learning in robotics right now. So we know that modern robots are precise enough to achieve very impressive tasks, like, for example, assembling cars. They are also resilient enough to operate in hostile environments, like, for example, in space. Like here is an example of a rover running semi-autonomously on Mars. And right now, it is even possible to fly on Mars with the new Ingenuity Mars helicopter that has been recently deployed and is now already finishing its operation. But surprisingly, fully autonomous robots taking care of mundane household chores, they're not there yet. And the routine tasks that humans can do, such as, for example, tending to the crops, they're also not yet fully automated. Now, why is this a problem? Well, one big problem is that the need for help with physical tasks is rising. We know that there is a big issue with population aging, so older people would require more and more physical help in their homes. And we also face various structural problems with shortages in terms of who can work in some of the sectors such as food production and agriculture. And here, to mitigate the labor shortages, we also need robots to be able to handle these challenging environments. All right. So now the problem here is that all these environments, all these so-called unstructured environments, everyday environments, they seem very easy to us humans. And so the paradox of robotics, so to speak, is that the things that we consider difficult actually are solvable right now, but the things that are easy for our everyday operation is a bit difficult for robots to do still. Okay, so what are some of the ingredients that we need to be able to handle if we want a robot that can learn in a self-sufficient manner? So first of all, the robot needs to be able to move. So we need to be able to handle locomotion or other ways of moving. The robot needs to be able to adapt. So for example, if it knows how to solve a task in one of the environments, then it should be able to handle similar environments that look different. It also needs to be able to handle unstructured scenarios and operate with different kinds of objects, for example, wires, sheets, clothing, fluids, and granular matter. And the robots also need to be able to explore to overcome the difficulties on their own without external help. So basically try various ways of completing the task in a that efficient manner, even if the policy that they are preloaded with is not able to solve the task initially. All right. So mobility, adaptation, and exploration, they come naturally to us human, but basically we take it for granted that they enable us to operate self-sufficiently in our surroundings. And so we need to be able to give explicitly these capabilities to the robots, and that's what I'll talk about further today. So first of all, probably learning from scratch is not a good idea. So we need to consider, how do we train these robots? So what are some of the environments that we can use for training? Well, we can use simulation, and we can also use real data from a related domain, for example. So you've probably heard a lot these days about so-called big data. We have big data in robotics as well, or at least starting to have that with a lot of visual data and also data collected by various companies right now. And so the question is, okay, what is the difficulties with just learning from real data, ignoring the simulation for now? Well, of course, as you can imagine, it is costly to collect the real data because you actually need a real physical system in order to collect it. There might also be issues with access rights to this data, depending on who collects it and who owns it. There are potential biases in the data, depending on how it's collected. There might be privacy concerns, again, if it's something like, for example, collecting data in personal homes or in hospital settings. And also, the data might be focusing only on a subset of tasks. So when you go and deploy the robot to operate in everyday environments, it might not cover that set of tasks. So these are the issues with real data. And so, as you can see, maybe training from real data is not enough. So one of the things that we can consider is simulation, because of course we can construct all sorts of, all kinds of environments in simulation. So here's one example. Let's take a look at bipedal locomotion. This is an example from a while ago, back when we didn't have humanoids so ubiquitously, and people were just getting an understanding of how bipeds could walk. But it's still relevant because I think conceptually it explains what needs to be done. So let's suppose we have this simulated environment of a bipedal robot, and we're looking into how to develop a method that would let it to adapt to transfer the policies to the real robot in a data efficient manner. Usually this branch of works is called sim to real. You might also have heard other kind of versions of this, but I'll refer in this talk to this as a sim to real transfer problem. And I will talk briefly about the family of methods that I worked on during my PhD that I called Bayesian optimization with simulation-informed kernels. So Bayesian optimization is a very well-established method, and ultimately it is data efficient, but I wouldn't say ultra data efficient. So not data efficient enough to, let's say, handle adaptation for a biped just in a few trials. And so I'll explain a few kind of conceptual works that I applied in this family of works. So at the beginning here, we run a large number of simulations of robot controllers. This can be done fairly cheaply. They can also be done in parallel, so it can be a large-scale data collection. And then we train a neural network to map these controllers to the predicted behaviors of the robot. And so what happens then is that what we can do is we can develop a kernel or a transformation of the space that will let us compare the controllers not based on their superficial, just floating point parameters, but based on the predicted behaviors that they induce on the target system. Of course, here the behaviors would be in simulation for now. But let's take a look at what this accomplishes. So here is a visualization of a two-dimensional slice of a cost landscape. And the yellow points here are all the settings of the controller parameters where the robot is falling, so very high cost. And then the blue points at the bottom, you can see there are the various costs that you get by robot walking in various ways at different speeds and with various gates. So when we learn the neural network kernel, what happens is in the transform space where we consider the behaviors of the controllers, you can see that all the yellow points are clustered very close together because robot just falls in slightly different ways at the very beginning of the trial. And then you can see that actually the blue points are kind of spread out across a wider range of the space. And so that gives us an ability to basically spend more time exploring useful parts of the space. But for now, useful according to simulation. So in order to close
can I ask
yes.
one question?
Yeah.
So you have this neural network that is mapping the parameters the controller parameters to this behavior. And my question is about how do you represent the behavior? What are kind of the variables?
Yes, great. Good question.
Yes.
So there are a few ways of doing it for specific systems, like, for example, for locomotion and grasping. These can basically measure, it's kind of like inspired by the trajectories. So you can measure where the robot is at a particular point in time and kind of record this as a trajectory. And then this will be kind of like a higher dimensional representation. Higher dimensional here is not too high, maybe 10 or 20 dimensions in terms of where the robot was at a particular point in time at some predefined intervals. Luckily, I have later on generalized this to being able to automatically embed longer trajectories sampled at high frequency into a lower dimensional space where you can still kind of view it as a behavior, but in a latent space. So ultimately, as you will see in the further follow-up work, what I would have is that it's sort of the representation is also learned automatically, and ultimately the behavior is just everything about the robot that you can record, like it's all proprioception data during the trial, and then you take that whole proprioception data and then you use a variational autoencoder in order to embed it into a latent space.
Cool, thanks.
Yeah, and here it is kind of explicitly sort of taking where the robot was at a particular point in time. This is like an earlier work, so that doesn't have this variational embedding, but then it's very easy to interpret. So that's why I'm using this for earlier work to describe in a visual manner what happens. All right, so yes, so now we need to close this interreal gap actually, because this space transformation is nice, but it just tells us about the kind of how to compare behaviors according to simulation. And so what we do is we put this into the Bayesian optimization framework, where now the Bayesian optimization, instead of a standard kernel, is using the simulation-informed kernel. And we run a trial on the real robot. We get the real result. We add the result to the posterior. I will explain visually kind of what does it mean to have a Bayesian optimization in a Gaussian process posterior. And then we repeat again and again and again. And in 10 to 20 trials, we're able to have a walking controller that is capable of recovering from failures that arise due to septorial mismatch. So very briefly now, probably there's a lot of people in the audience who are familiar both with Bayesian optimization and with Gaussian processes, but for those who maybe haven't seen it before, I will very briefly introduce the concept. So this is just a general background. You can see Bayesian optimization as a method that has as a goal of finding points that optimize a certain objective. So here, this kind of blue band represents our Gaussian process posterior. It doesn't have to be a Gaussian process. It basically just has to be something that keeps track of our kind of posterior mean over the prediction of what would be the outcome given the input, and also the uncertainty. So Gaussian process is useful for that. So on the x-axis, we will have controller parameters. Here it's just a one-dimensional example, but ultimately, of course, we're dealing with higher dimensions. On the y-axis, we will have some sort of objective function that we're optimizing. In this example, it's just going to be the cost. Cost of, let's say, running the robot in terms of kind of wear and tear, and also cost in terms of, okay, did the robot fall or did the robot walk at an appropriate speed? So you can construct like a simple cost function like that. And our controller parameters, they can be very kind of structural and explicit, like, for example, explicitly the target velocity for the controller or the target stride length, like how far the robot should step, or they can be very implicit if the controller is, let's say, much more high level, it doesn't have a high level explicit parameters like that. Now, the point of Bayesian optimization is to track uncertainty globally while also systematically exploring the unseen region in the space. And here at the center, you can see this red cross. So this is like the first trial that we have tried on the robot. And we know right now that for a parameter input of, let's say, close to 4.5, we have the response of the cost that is close to 0. And this is what our posterior is going to look like after that first trial. So I will go through one-dimensional example of this very quickly. So this is our first trial, and this is just a visualization, a one-dimensional visualization of how the Gaussian process posterior would look like. Now, our acquisition function would tell us to sample next in the part of the space that is highly uncertain. So we would first work with reducing uncertainty. And after a while, we will start coming back to the places where we actually see a lot of promise. So there is a high probability that we will kind of get some observation that is better than all the previous observations. And actually later on, we would leave some of the regions underexplored if they don't look promising enough in terms of their uncertainty band, and we will keep coming back to the regions that are promising. So this is, for example, for the case of the cost minimization, we will keep coming up to this low cost region, and eventually we'll find something that is close to the optimum. Now, formally, what we're using here to track the uncertainty is a Gaussian process, which is a stochastic process, and technically is an infinite collection of random variables that are indexed by time or space. And here we're indexing by space, so that's our x-axis, and our space is the space of controller parameters. Now, the Gaussian process is a type of a stochastic process where every finite collection of random variables is jointly Gaussian. And usually when I kind of introduce this in the talks, people ask me, oh, Gaussian, does this mean simple? And I want to emphasize here that in this case, Gaussian does not mean simple. What happens is that when you're considering this joint distribution, is actually the joint distribution of whatever subcollection of variables you consider. So this can be very high dimensional. And the flexibility of how these variables relate to each other, that has to do with how many trials you have sampled and what was the response during the trial. So ultimately, this posterior is highly flexible. All right, so this is the sort of the formal part of this. And then one important piece in Bayesian optimization and in Gaussian process specifically is something called the kernel. So the kernel basically determines the region of influence for a sample point. So if we sample a point, what can we infer about the neighboring points? And they effectively incur distances or equivalently similarities between the points in the search space. And one of the limitations usually that we face is that most kernels, they rely on simple Euclidean distances. So, like the form that you see there, which is a squared exponential kernel, which is basically takes some parameters times e to the minus the distance between the points. And then this distance is usually Euclidean. And even if you have slightly more advanced kernels like the family of matter kernels and the other kernels, they are frequently stationary, meaning that even if they adjust parameters, let's say in different dimensions, they still ultimately kind of base their decisions based on the distances between pairs of points. So what I will advocate here in this family of works is that what you can do is you can learn transforms, kernel transforms from simulation. And effectively, this will remove your stationarity because the kernel transfers will then measure the distances according to the not all flat controller parameters, but the behaviors that they induce, at least as reported by simulation. And of course, you would use something like deep neural networks with various architectures in order to be able to generalize so that you're not only able to measure distances of the simulated trials that you have actually collected in simulation. So that's kind of the motivation for a few of these of this line of work and a few papers that were published in this line of work. So coming back to bipedal locomotion, I will illustrate how this actually worked out on real examples. So this is the Atreus biped that that was our experimental platform, and it's at Carnegie Mellon University. So here the point is for the robot to walk. You can see the robot is supported by the lateral boom, but it is not actually holding it up. It's only supporting it if it falls. So here with just a few trials, so 6 or so trials, we're able to find the walking gaits for the robot that enable it to go round and round and round without falling. Whereas if you just use, so this is with the Bayesian optimization with simulation informed kernels, whereas if you just use Bayesian optimization without the informed kernels, then you take much, much longer in order to be able to find walking gaits. So we have experimented. Oh, sorry, was there a question? No. So we've experimented with a few versions of these of the kernels, and ultimately they're fairly simple network architectures that are capable of learning this kernel and using the simulator that we've had for this robot. Now, the interesting part is that this platform, okay, it looks ancient right now. This was just a few years ago, but the pace of development in robotics is picking up right now. So there are already 2 successors to this robot, and one of them is the Digit, which you might have seen. Amazon recently signed a deal with the Digit in order for the Digit to be able to work in Amazon warehouses. So you can see that the legs of this robot are actually being used already in production. All right, now this was for bipedal locomotion, but this algorithm and idea in general is not specific to that class of problems. You can do very different kinds of, you can solve very different kinds of problems in robotics with this. So for example, I had a line of work on task-oriented grasping where there's a similar idea. You take an input, in this case, a point cloud from collected from the depth camera, and you pass this during the Bayesian optimization through Bayesian optimization with the informed kernel that has been constructed from a lot of simulated grasps. And here we can learn to predict the grasp stability and suitability for a given task, because it's a task-oriented grasping, so you have to grasp an object in a manner that is appropriate for the task. And if you fail the first time, then you're able to quickly adapt then by using the Bayesian optimization framework. Here, our simulators tend to be much, much less precise, maybe surprisingly, than for a biped, because there are a lot of contexts, and there are a lot of unobserved things like friction, for example, that is completely either not modeled or not observed. And so what we need to do here is we actually found that we need to mix in basically a sample from both the informed and uninformed kernel, and additional samples from uninformed kernels actually let us ensure that we are robust to systematic simulation inaccuracies, and we're still able to provide kind of increase in data efficiency while not being misled by the systematic inaccuracies in simulation. So these are a few examples of how this actually works in practice. So a few of the objects the robot is able to pick up, for example, for this handover task fairly easily. So I actually focused on the objects where we specifically had issues like slippage or inability of the robot to initially plan a good approach. And with the Bayesian optimization with simulation-informed kernels, you can see that very quickly after the initial failures, the robot is able to successfully complete the task. And furthermore, I also wanted to check, so this is a kind of a wider test on a larger set of object task pairs. But with that, I also wanted to check what happens if we have highly degraded kernels. So not just regularly inaccurate like we have in practice, but what if we had some kind of systematic problem with the kernel? So here, if you just compare to vanilla Bayesian optimization, then you can see that we can achieve success fairly quickly with a few trials. So that's good. You can see a very big separation there. But what happens if you have a faulty kernel? So this black line here shows what happens if you start using the faulty kernel that is degraded on purpose even more, just to test the robustness to that. And you can see that initially the black line is actually doing a little bit worse than vanilla Bayesian optimization, which is expected. But then it overcomes the negative transfer fairly quickly when we sample kind of alternatingly in an alternating fashion from the informed and uninformed kernels, and is actually able to recover fairly well. So ultimately, coming back to the question of how the behaviors of the robot are represented, to generalize this set of works, what we have done ultimately, if we've developed a way to build the latent representations of the trajectories so that we can kind of run the Bayesian optimization with the kernel that is in the lower dimensional space, but it's actually automatically kind of like embedded from the higher dimensional space, which could be very long trajectories. And so here, this embedding is learned using sequential variational autoencoder, and that automatically gets the compressed paths, I call them latent paths, that embed the longer trajectories. And the good side effect of this is also that we're able to then adapt the relationship between the control parameters and the latent representation online during the Bayesian optimization as well by propagating the gradients through. And this is possible kind of as the contrast to the frameworks that just propagate the gradients all the way through to the kind of like lower layers of the neural net. And in the case where people do it end-to-end, kind of like without this modular framework, compared to that, the modular framework is much more data efficient because you can just adapt the latent embedding part and not touch the original like higher dimensional trajectory. All right. So we have applied this just to check that this works, for different kinds of problems in robotics. We have applied this to the problem of learning to walk on this hexapod robot, and also to the problem of non-prehensile manipulation, where this manipulator on the right learns to push the paper towels to the center of the table. And so we can see that within a few trials, again, with this framework, but now with the embeddings learned automatically, we're able to get to basically successful tasks, even if we have a lot of failures at the beginning. All right, so this was about the sim-to-real problem, but the problem assumed that we had some sensible simulator to begin with. But there are cases where actually simulation is quite far from reality, to the point where you might want to adapt the simulation first in order to resemble the reality a bit more. And those cases arise when we need to manipulate with deformable and highly deformable objects. So what can we do in this case? So this problem, I will address it as real to sim. In the earlier days, some kind of similar problems were called there were other names for these problems, but for now we would refer to it like system identification, for example. But now I will refer to it as a real to sim. And one of the things that we can do is we can use differentiable simulation in order to adapt directly the behavior of or the parameters of the simulator to the observed environment. So overall, what is the promise of the differentiable simulation is that we have a function f of x, which is the actual simulator, but then the simulator is basically built. So it's a program, but it's built in such a way that you can propagate gradients through that program directly. So it's not necessarily, or usually I'm not going to be talking about the neural net here being this f of x. Here, f of x is an actual physical program. It's just structured in such a way that you can propagate the gradients through it. So what is this good for? Well, first of all, you can back propagate all the way to the physics parameters of the simulator and hence adjust the physics parameters so that the behavior that you observe actually resembles what you have in reality. You can also adjust policy parameters. There is a way to set it up in such a way that you back propagate so that you adjust the policy parameters and hence change your controller behavior. And you can even set it up in such a way that you learn morphology or you adjust the geometric parameters of the problem as well. So we have worked on all three parts of this, but here I will highlight how this actually works for the real-to-sim to learn the physics parameters. So you might think that overall, kind of just using this concept, the problem is solved. Once you have a program through which you can propagate the gradients, then you are done. But actually, the cost landscapes, they look somehow a bit similar to what I'm showing in the images here. And you can see that they're pretty rugged. So just a single gradient descent is not going to be able to do very well here. So in one of the recent works, what we've done is we've introduced hybrid optimization method that combines the global search, semi-local population sampling, and then gradient descents. And we have showed that, okay, now it can operate on landscapes like this, and it is able, for example, I'm showing examples here on the right, to infer the parameters of the elasticity parameters, the mass, friction, sizes, so the parameters to be able to align, for example, cloth of different properties. So like highly deformable cloth collapsing when you lift it up versus slightly more stiff cloth that does not collapse. So you can also actually use the same framework in order to optimize the policies. And we have a few of the simulated environments that we have developed that people can also use to test. And we have shown kind of how this works with a few real examples as well. Ultimately, what you can also do is you can close the loop all the way, not needing the mesh, but also being able to use high dimensional observations like point clouds, for example. So if you have a simulator that works off of the mesh states, what you can do is you can use a differentiable point cloud sampling in order to back propagate the loss that is based off of just a point cloud. So for example, it's a modified version of a chamfer distance that you can propagate all the way back. And again, we have shown that you can do the alignment in such a way that you can infer the properties of the cloth. And in this case, take the input directly from the camera. So now you can kind of close the loop with the real world right away. And that works much faster and is much more efficient than, for example, using a non-differentiable simulator where you first collect a large amount of data and then you train some sort of a big neural net in order to kind of interpolate that data and so on. Here you can do this optimization directly. But the problem is not fully solved yet, because when you have rigid context, for example, if you show the kind of slices of the cost landscapes that these problems generate, they would look kind of not very pretty, as you can see there. So you might imagine that even a hybrid search will not be able to get out of the very, very challenging kind of plateau areas. And even if you simplify this problem to have very few contexts, you still have the fundamental kind of issues here being present. So then, because of this, I've also looked into, okay, if you're dealing with such scenarios, what can you possibly do in order to improve this? And potentially maybe using a non-differentiable simulator as well. So now I'll briefly talk about that. So one of the ideas that I've explored last year was to use distribution embeddings in order to represent the state of a deformable object. And with that, be able to kind of account for high uncertainty and variability in how the deformable objects behave. So the idea is that you start by collecting a lot of the simulation parameters from some sort of a prior. It can be a uniform prior. And here I'm showing an example where we're just keeping track of 4 classes of parameters: bending stiffness, elastic stiffness, friction, and scale of the object. And this illustration that you see there is actually simulation. So the background of it is a real image because the background is not changing. But the rope that you see kind of being manipulated there is a simulated rope. So one of the things that you can do with this is you can extract the key points of the motion of this rope, and you can use off-the-shelf unsupervised learning methods from computer vision to do this. They're pretty good already in order to keep track of the overall motion of the robot, of the rope. But the problem with them is that usually these key points, they arrive to you in kind of an unstructured way. So they're unordered, they can appear on different parts of the object, they can jump around across the different parts of the object. So in this work, we've proposed a representation that would embed these kinds of key points into an infinite dimensional space. So basically seeing these key points as samples from a probability distribution that represents a shape of the object, and then use distribution embeddings that you can actually define on just a sample-based kind of evidence. Use this in order to represent overall the state of the object in this kind of like embedded space. And what does this give us? So this gives us a permutation and variance, a kind of by construction. We've shown that it is robust to noise, so noise in the sensing, which is the actual problem that you have if you're using real cameras. You will also get a convenient distance metric, and whenever you need kind of algorithms that rely on distance or similarity metrics, they would benefit from this. And it's actually nice to analyze these things mathematically because you can kind of show various continuity results for this mapping. And you can also compute all of this fairly efficiently, for example, with random Fourier features. And in this particular work that we've published in 2022, we've shown how to also adapt the representation of how to do this embedding efficiently, for example, with random Fourier features, in order to be able to kind of customize this representation to the current class of inputs that they're dealing with. So roughly, you can then plug this into your kind of inference pipeline. So you can use any kind of inference method then in order to work on this representation. And to close the loop, after you've run the inference for the simulation parameter, or rather, after you've kind of selected the inference method you will be using, you can give as input to that method the real trajectories of your system, and they will help you to infer the simulation parameters that align better between the simulation and reality. So we have a few experiments, but I'm showing this just one example here with this winding task, where on the bottom you can see the on the right hand part of this, you can see the plot where on the bottom there are 2 methods that are using this RKHS embedding that we have proposed. And you can see that there is a big gap between that versus not using that embedding using kind of a fairly standard inference method. So we have also kind of tested this on a range of other tasks with deformables, and we have seen that, okay, now this idea actually lets us handle this real to sim problem even without being able to differentiate through the gradients in the simulator. All right. So now I've talked about a few ways that we can align the simulation to reality if we're starting with the simulator that is too far from reality. Once we have a sensible simulation, we can do various optimization methods in order to find the controllers that are effective. And also at the beginning of the talk, I talked about how you can use the Bayesian optimization with simulation-informed kernels in order to then close this interior gap if your controllers don't have a zero-shot transfer right away. And I think one of the kind of important pieces here is to explore a few more methods in data efficient learning. They're maybe not only based on, let's say, Bayesian optimization, where you'd need a kind of a more structured controller parameter space to search over, but actually can just learn controllers from scratch. So talk about one of such lines of work now. And in this line of work, we leverage equivariant architectures in order to get the data efficiency. So the idea here is that if you have a few examples of how to solve a task to a human, they can extrapolate how to solve this task with objects of vastly different appearances and sizes if the concept of the task is still the same. And so we want to do something like this for robots. So we want to generalize to unseen appearances, scales, and object poses. And the concept of the task is the same, but actually how you go about solving the task is slightly different. And of course, the visuals and kind of the perception of the task is very different. We want to be able to handle various kinds of objects, rigid, articulated, and soft objects. And that we can actually try to do with zero-shot transfer and see whether we can do this kind of right away without further adaptation. So in this method, we have two phases. One of the phases actually first pre-trains our representation to be able to handle deformables well. So for this, we have point clouds as input, and then we use vector neuron architectures introduced in a CVPR a few years ago, but also modified in such a way that we can have additional training that works well for non-uniform rescaling and also working with non-rigid objects. And then we use a contrastive loss in order to pre-train this on a lot of different simulated rollouts with our deformable objects. And then the second phase, we learn a policy, just given a few examples with the behavior cloning, we learn a policy that is good for solving that task. And then the equivariance in the architecture gives us an ability to solve this task for objects of vastly different sizes and appearances. So I will not go too much into the detail, but basically here for the training part of it, there are a few vector neuron layers that are taking care of the equivariance. And there is a particular way to output the actions for the robot and kind of be able to have those actions inform which part of the stage of the task the robot is supposed to be operating in. So right now, what we do is we kind of work with end effectors of the robot kind of being able to open and close and grasp the object, and also kind of the action map that is generated that overall tells the robot kind of like what it is supposed to do, given an input state of the object, where the input state is just a point cloud observed in the environment. So this is actually our environment, and these are experiments done at Stanford. We have a few of these mobile platforms, each has an arm. We have ceiling cameras that can give us a depth image, and some object can be articulated object or deformable object in this case. That's what we've tried. These are on the top, you can see the demos collected. So just a few demos of a person manipulating with a small object. And on the bottom, you can see the rollout of the policy on a much larger object. So this is the difference in the comparisons of the scales and the visual appearances. And these are examples of kind of contrasting how the method on the right, which is the equivector method we've developed, works compared to some of the baselines that are not using the architecture that we have proposed. Right, so we can learn a few multi-stage tasks as well, such as closing the box. And we can also operate on, obviously, objects of different scales because we have these freely moving mobile platforms. All right, so with this, you can also go further and do things like incorporate large vision language models that can parse out the full scene. So maybe not paying attention to just a single object, but being able to basically figure out where all the objects are in the environment. And this is recent work that we have done that's called TidyBot, where the robot tidies up the environment, giving the user preferences for where the objects should go. The robot roams around the space, finds these objects, and puts them in the appropriate locations. So here, there is a combination here of the what you can do with the infrastructure type things that are already developed by other people, like, for example, the large vision language models that can parse out the scene, and the, the robotics specific things, which tells the robot of how to behave. And you can clean up the mess in the sense of sorting out the laundry, or you can do also fine manipulation by placing small items into the corresponding receptacles. All right, so to conclude, I want to find interesting things to do at Cambridge as well. So I'm starting a lab that will definitely bring in some new hardware, and ultimately I'm interested in working with multi-robot teams that are heterogeneous. So you have maybe mobile manipulators, you have some locomotion like either quadrupeds or other systems, and I'm also looking forward to interacting with other people, like Amanda Prorock, for example, in my department, and she's working on aerial systems like drones. So putting all that together would be really nice. I would also like to explore co-evolving the hardware for now, the sensing part of it, with the learning methods. So we have a lot of different kinds of sensors in robotics, but it is ultimately not particularly clear which of them are useful and crucial when learning the task. And so I want to apply some of the ideas that I've developed in terms of global optimization in order to kind of iterate on understanding which of the sensors and what are the sensor properties are important for the task, and then evolve the design or the placement of these sensors as well. And there are a few things that are not directly related to robotics that I also want to pursue, like, for example, figuring out efficient strategies for agriculture, using reinforcement learning, for example, improving the efficiency of residential buildings, for example, in terms of their power consumption. So these are the methods that also need to be highly data efficient, but they're not necessarily in robotics in the sense of there's some moving part there, but it's kind of algorithmically a similar idea of just having very few data points and needing to influence a real system. Ultimately, there are also interesting problems that have to do with climate modeling. Again, there is a sim-to-real problem there as well. And lastly, I'll just mention a few things that I'm already working on, and there are projects that I'm continuing with going forth. So there's a collaboration with the University of Waterloo where we're looking at neuromorphic Bayesian optimization, which can actually work on highly resource-constrained hardware. So ultimately, for now, our work here is algorithmic, but actually this group is dealing with neuromorphic chips. And so ultimately, we want to be able to place this and be able to be not only data efficient, but also power efficient and computation efficient. And lastly, we've recently had a collaboration with NASA Astrobee team. So you can see there are these little Astrobee like cube robots that are floating on the International Space Station. And they have recently added like a very rudimentary arm to them. So they're now capable of doing kind of basic manipulation. So what we want to look into is how to transform deformable bags with these robots. And, you know, this would draw from a lot of the previous expertise that I have on manipulating with deformables. But of course, now in this much more challenging environment where you can't just randomly explore, you need to come up with methods that explore in a very kind of in a way that guarantees the safety constraints are satisfied. So with that, I think that I will close this and then hopefully get some questions from the audience.
Good. Thanks. Thanks a lot for the presentation. I think if anyone wants to ask questions, I think you can just probably unmute yourself and ask the question. You can also write questions in the chat if you want to do it that way. Maybe I can start with some questions. So I saw these kind of surfaces where you were doing optimization, and they look really ugly.
Yes, they do.
Could you, could you give some insights on why specifically this looks so challenging? What is kind of that? I mean, why do you get these kind of patterns? Is it because of noise, or what is the thing that is kind of producing these non-smooth surfaces?
Right. So unfortunately, it's not noise because these simulators are actually deterministic. So there are two main sources. The first major source is basically contact dynamics. So if you have rigid contacts, then obviously you have issues where you basically have transition. It's like usually called like hybrid systems. So you like transition from one mode to the other. So you observe this with friction as well, but a lot of it you can observe with contact. And the reason why these surfaces look so ugly also is because usually we consider what's called contact-rich scenarios, where you have multiple contacts and they all transition kind of from no contact to contact. So you're transitioning from kind of the smooth part of the system to the rough to the, again, kind of like smooth part. And so that's kind of roughly how we even expect them to look. But still, you expect that on the sort of smooth parts of the system, you can gain a lot by propagating the gradient. So you can actually have a very good kind of performance in the parts of the space where you don't have this contact-rich interaction. So that's kind of like the major source of problems that comes in. Another part of the problems, of course, if you have, for example, here I'm showing the interaction of a deformable and the rigid object, and here the contact is kind of not really rigid because you can model the contact as deformable, and there it depends on how you structure your simulation. So, for example, mesh-based simulations that also still retain some kind of non-smoothness, they result in surfaces like this. But if you have a particle simulation, you can have much smoother surfaces, but then you trade off the computational performance versus the niceness of your landscape. So if you have many particles, it's kind of like the whole computation smoothes itself out, especially if you're working with deformables, but then you are 1 or 2 orders of magnitude slower in doing the forward and especially the backward path. So that's sort of the 2 sources of challenges there.
Mm-hmm. Good, thanks. Let's see if anyone in the audience has any questions. You can unmute yourself if you want to ask anything. No more questions? Okay. So yeah, maybe one more question. Yeah, you have been talking about these methods of Bayesian optimization. And obviously, I think they can be successful in settings where you can collect some enough amount of data to solve your task. I can imagine on these interactions with real-world robots. No, so maybe you can collect data. I don't know. I can imagine maybe hundreds of data points or so at most. I can imagine that in many tasks, maybe you need actually many more data points than just hundreds. What do you think would be the approach there? It's do you need to rely maybe more on simulations to reduce that, or what
so
your thoughts in those settings? Maybe I'm thinking about more challenging settings where you really need to do more trials than just maybe, I don't know, like a few hundred or so at most 100 that you typically do with Bayesian.
Yeah, so I think there is a kind of a dichotomy here. So these classes of tasks that I have shown with the, which involve the Bayesian optimization with simulation of formed kernels, I call this now the whole kind of method ultra data efficient because most of my results are in 10 or 20 trials, you are able to solve the task, even if at the beginning the transfer wasn't there. But of course, that is accomplished, in large part by collecting the data in simulation that informs you about the space. So the big question there is, okay, how can you work then without the simulation here, right? Because if you literally start from scratch, then where would the information about how the shape is structured come from? And so because of this, I'm kind of thinking of this as sort of two cases. So one case is if you have imprecise simulations. I've shown how you can use imprecise simulations to really significantly bring up the data efficiency of BO. So then you don't need hundreds of trials even, you can do just 10. But if you don't have simulation, any simulation, like even the unaligned simulation, right? Then I'm betting more on putting kind of the smartness in principle into the network architecture itself, right? So for example, here, the architecture itself being able to kind of leverage equivariance gives us a very significant boost in the data efficiency, so that when you learn from, let's say, 10 trials, it's as if you've had 1,000 trials, right? And if you have 100 trials, it's as if you had 10,000 trials. So it's basically improves the data efficiency by 1 or 2 orders of magnitude because it now doesn't need to see all of these variations of, which perspective you have seen the object with, what was the scale of the object, and so on. And so I think this kind of thinking of how can you bring in, so like symmetry, for example, is I think, one of the next frontiers, how you can bring in some mathematical concept that we know would improve the data efficiency and build them into the network architecture itself. And there's some reason to believe that actually it's not a lot in the pre-training that is needed here. And this is like new work that hopefully will be coming out at some not too distant future. But actually a lot of the power is in the architecture itself, so that you can pass just a few examples through that architecture, and that will be able to kind of like extract the maximum amount of information from.
Cool. Good. Thanks. I think that's probably all.
Oh, there's something in the chat. Oh, no, this is something different. No.
Okay.
I thought there was a question in the chat, but no.
Yeah, it's a question about the talk. The talk has been recorded, and we'll put it in the YouTube channel that we have for the seminars from the unit. So the talk will be available there. Cool. Thanks a lot, Rika, and we are looking forward to see you around in Cambridge very soon.
Great. Looking forward to that.
Good. Bye. Bye-bye.
Bye.